and thanks for listening. Welcome to the Terran Space Academy. Please don't forget to like and subscribe, and help support us on Patreon if you can. We also have Academy-themed merchandise available. There are links in the description for these. Sometimes, after a lesson with a lot of equations, we like to create one with fewer numbers. One you could sit back and just let your brain absorb. In our lesson describing the launch, orbit, and landing of the Starship, I gave a description of an orbit. I showed a spaceship in a stable orbit, being pulled toward the center of a planet by gravity, but having enough horizontal velocity, relative to the planet, for the centrifugal force pulling the ship away from the planet, to balance the gravitational force pulling the ship toward the planet, thereby allowing the ship to move in a circular path around the planet, essentially forever, unless another force, like atmospheric drag, acts on the ship to change its status. I received feedback from one learned colleague that this was a disservice to the class, as there is no centrifugal force, and that this is only a fictitious force. They are wrong, but they are also right. Orbital mechanics are complicated, and physics itself can be mysterious to understand. There are, in fact, in the entire known universe, only 4 forces proven to exist: the strong nuclear force, the weak nuclear force, electromagnetism, and gravity. Centrifugal force is not included. Neither is centripetal force. But what physicists call a force, and the common meaning in usage, are not always the same. If no other forces exist, then what kills us in a car crash? It's not gravity. It's certainly not nuclear. We didn't suddenly become magnetized. To understand these principles, let's go back to those forces, and then into the laws of motion. Remember that, in science, a theory is above a law. A law tells you what happens. A theory tells you why. Scientists don't use the word theory to mean a guess or supposition. That is what they call a hypothesis. To scientists, a theory is an explanation, describing observations with sufficient data to support a belief in its accuracy. Theories are often incomplete. They must, when new data contradicts old data, be modified so as to accurately describe the new information, or they must be discarded altogether. Newton came up with the laws of motion and gravity, but he didn't know why. He made some guesses, but these turned out to be wrong. Scientists, armed with Newton's laws, collected data and applied the equations provided by Newton to that data. For almost everything, Newton's equations worked perfectly, but not for the orbits of Mercury and Venus. There, the predictions described by Newton's equations failed. Einstein examined these failures and expanded Newton's theories, providing equations that argued that at extreme velocities, or under the effect of extreme gravities, Newton's laws failed, and his equations gave faulty answers. Scientists applied the expanded equations of Einstein to the motion of these planets and evaluated the solutions against the observed orbits of these planets. And their data matched Einstein's predictions, proving his theory correct. Einstein did not win a Nobel Prize for one of the greatest accomplishments in human history. He won a Nobel Prize for accurately describing the photoelectric effect, where photons throw electrons off atoms and create a current. Einstein's theories of general and special relativity describing the effects of extremely large masses and velocities, along with the theory of quantum mechanics describing the actions of subatomic particles, are the most proven theories in science. But even though they accurately predict what we see in the universe in almost every case, they are both incomplete. Both of these theories fail when extreme mass and gravitational force are compressed to subatomic dimensions, like in a black hole. There is still more to learn. Someone, human or not, or even an AI, somewhere, maybe tomorrow, maybe thousands of years from now, will unify these theories. Until then, we see 4 forces. Each force has its own set of equations. At one time, we saw 5 forces: the strong nuclear force, the weak nuclear force, the magnetic force, the electric force, and gravity. But James Maxwell was able to combine these forces, from 20 equations, eventually down to 4 partial differential equations, combining the forces of electricity and magnetism into the electromagnetic force. Others since have tried to combine the rest of the forces, hypothesizing an electroweak force or electrogravity. None of these have sufficient data to support a belief in their accuracy. But if these 4 are the only forces, what caused me so much pain as a child as the dodgeball impacted my head? The dodgeball was following the laws of motion. There are 3 laws of motion. In the first law, an object will not change its motion unless a force acts upon it. A moving object will continue moving, and a stationary object will remain stationary. The second law states that a moving object has a force equal to its mass times its acceleration. What do they mean here by force? This is not synonymous with the 4 fundamental forces. The descriptor is used to denote something capable of affecting a change in the behavior of other objects. The third law says that when 2 objects interact, they apply forces to each other of equal magnitude and opposite direction. Let's look at that dodgeball, moving inexorably toward my head. The dodgeball has a mass, around 410 grams or 0.410 kilograms on average, 10% less than 1 pound for my imperial friends, and a velocity, let's say 50 miles per hour, which would be 80.5 kilometers per hour or 22.4 meters per second. This gives the ball a momentum of 9.18 kilogram meters per second. We say the ball has kinetic energy. The average human head has a mass around 4.5 kilograms. My head, to be perfectly honest, is probably closer to 5 kilograms. My head, however, is sadly not moving in this scenario, and the ball impacts my surprised expression-wearing head. Now some of the ball's momentum is transferred to my head. We have 9.18 kilogram meters per second impacting 5 kilograms at no meters per second. The second law said that force equals mass times acceleration, but at this point we only have velocity. We don't have an acceleration. Acceleration is a change in velocity over a change in time, or delta v over delta t. Over what time will the velocity of the ball change? The time it takes for the ball to slow down will depend upon the elasticity of the surfaces impacting. The ball will flex and give, as will the skin of my face, but when the skin is compressed as much as it can, the bones of my head will not compress as easily. The side of the ball impacting will also deform, but when it reaches the limit of deformation, it will also refuse to yield further. Let's say it takes 1/10 of a second for the ball and my face to reach the limits of their deformation. This would mean that the velocity of the ball traveling 22.4 meters per second came to 0 over 0.10 seconds. If we start at 22.4 meters per second and go to 0 meters per second, we have a change in velocity or delta v of 22.4 meters per second. We put this over the delta t or change in time, which was 0.10 seconds, and end up with 224 meters per second squared. This is our acceleration. Force equals mass times acceleration, so we multiply the 0.410 kilograms of the ball times 224 meters per second squared, and we get about 92 newtons. The third law said that 2 interacting objects will apply forces to each other of equal magnitude but opposite directions. If force equals mass times acceleration for both sides, we can write this as mass 1 times acceleration 1 equals mass 2 times, we'll say negative acceleration 2, since it's in an opposite direction. If the ball decelerates, then my head will accelerate. This force will be transferred to my head on impact. My head has a mass of 5 kilograms, an advantage in this scenario. We can write this as 0.410 kilograms times 224 meters per second squared equals 5 kilograms times negative a. Or we can reduce the equation on the left to the force, getting about 92 newtons as before. We can solve for minus a by dividing both sides by 5 kilograms. This gives 18.4 meters per second squared. This is the acceleration felt by my head, resulting from the transfer of momentum. We know that acceleration equals change in velocity over change in time. We can arrange this equation to solve for time if we know the acceleration and resultant velocity. Time would equal dv over a, or for velocity, if we know the acceleration and change in time, dv would equal a times dt. A equals 18.4 meters per second squared. Multiply this by the 0.10 second delta V, and we see that my head starts moving away from the impact point at 1.84 meters per second, or about 6.62 kilometers per hour, which is 4.12 miles per hour. Why so slow? My head is more than 10 times the mass of the soccer ball. It seems reasonable that the velocity change would be more than 10 times less. Luckily, like most former Marines, I have a very thick neck, and will assume that my head stays attached. If the ball were hollow, of the same mass, but made of steel, it would not deform on contact with my face. That would cause the transfer of momentum to occur over a much shorter time, generating a greater acceleration and therefore more force. Rockets burn oxidizer and fuel to create heat. They bottle the heated resultant chemicals and focus them in one direction. The departing momentum of the propellant creates an opposite and equal force, pushing our rocket through space. In this context, the term force is not describing one of the four fundamental forces. Let's look back at those four forces again. 3 of the 4 forces have a known particle proven to exist that transmits or carries that force. Gravity is the exception. We'll save it for last. These force-carrying particles are called gauge bosons. The strong force is carried by gluons. The weak force is carried by W and Z gauge bosons, and electromagnetism is carried by the photon. The strong nuclear force exists between quarks. Quarks are fundamental particles of matter. The strong force can only act over an extremely short distance, shorter by far than the radius of an atom. At a range of 1 femtometer, the strong force is 137 times stronger than electromagnetism. If we go too far outside that range, electromagnetism becomes stronger. When 2 protons are brought together by gravity in a star, remember that a single proton is a plain hydrogen nucleus. The similar charge causes electromagnetic repulsion. By squeezing them together hard enough, the star can get past that barrier and get them close enough for the strong force to take over. They then slam together and become a diproton, giving off energy. This is the first step in hydrogen-burning star fusion. The protons are made of quarks. Quarks come in 6 types: up, down, top, bottom, charm, and strange. For each of these, there is also an antiquark. Protons are made of 2 up and 1 down quark. An up quark has a charge of 2/3. 2 of them would be 4/3. The down quark has a charge of -1/3. That gives an overall charge of 3/3 or +1 for the proton. An antiproton would be 2 anti-ups and an anti-down, giving -4/3 and +1/3 for an overall charge of -1. Particles of matter made of quarks are called hadrons. Hadrons made of 3 quarks are called baryons, like protons and neutrons. Neutrons are made of 2 down quarks and 1 up quark, giving an overall charge of 0. If you hit a nucleus with a neutron at the right speed, the strong nuclear force will snap the neutron into the nucleus. This nucleus might be stable. Nuclei with the same number of protons but different numbers of neutrons are called isotopes. Carbon-12 with 6 protons and 6 neutrons is the most common form of carbon, and it is stable. If we add 1 neutron, it would become carbon-13, less common but also stable. If we hit it with another neutron, forming carbon-14, it would be unstable and decay over time. As you see here, we can hit an atom of uranium-235 with a neutron, briefly forming uranium-236, which is not stable, and decays to krypton and barium, giving off more neutrons. These neutrons can go on to hit other uranium atoms, 235 or the more common 238, and start a chain reaction. This is nuclear fission, and this process powers nuclear reactors. Uranium-238 is not radioactive enough by itself to cause a chain reaction and must be enriched with the more radioactive 235 to be useful as nuclear fuel. Here you see the uranium formed into pellets. About 3% 235 is enough to start the reaction. And here you see the pellets being assembled to be put into rods. These rods get extremely hot from the radiation. They can be bundled and used in a nuclear thermal rocket, which may be used someday to get us to Mars and the rest of the solar system much faster than chemical rockets. These rods can also be combined with thermocouples to produce electricity in a radioisotope thermoelectric generator, or RTG. These power the rover's Curiosity and Perseverance exploring Mars now, and may be used to help power off-Earth colonies in the near future. Some radioactive elements give off lots of neutrons as they decay. This is called neutron radiation, and is one of the most dangerous types of radiation. One element that gives off a lot of neutrons is californium, and it is sometimes used to jumpstart a reactor. Neutrons by themselves are not stable, and break down by the weak nuclear force into a proton and a high-speed electron within a little more than 10 minutes. The high-speed electron can cause damage too, and this is a form of radiation called beta radiation. The high-speed electron is called a beta particle, and this process is called beta decay. Beta decay is mediated by the weak nuclear force. Here we see a W- particle mediating this transition. This would make a radioactive element like carbon-14, which has 6 protons and 8 neutrons, break down into a new atom with 7 protons and 7 neutrons. Since the number of protons determines the element, this new atom would be nitrogen-14, which is stable. Here we see this breakdown process. Carbon-14 is usually produced in the atmosphere by neutrons, generated by cosmic radiation striking the Earth's atmosphere. These neutrons will usually strike nitrogen-14 atoms, since almost 80% of our atmosphere is nitrogen, knocking out a proton, which now becomes hydrogen, and forming carbon-14. Living things breathe this carbon-14. The carbon-14 is used in their tissues, breaking down and being replaced until they die. When an organism is no longer breathing, the carbon-14 decays but is not replaced. Knowing the ratio of carbon-14 to carbon-12 and 13 in a dead specimen, and knowing that the half-life of carbon-14 is 5,730 years, plus or minus 40 years, can help you know when something died. Someone might bring us a lambskin Egyptian manuscript, claiming it was made before the first dynasty, which would make it older than about 3,100 BC. We can test it, and if it has half the expected carbon-14, we can know that it was made before 5,690 years ago, indicating it might be real. If it has 1/8 of the carbon-14 gone, we know that it was made much later. If the lamb was running around 1,000 years ago breathing, the manuscript is fake. The carbon-14, due to beta decay, was emitting high-speed electrons. These high-speed electrons can be harvested for energy. An artificial diamond made of carbon-14 would produce power for a long time, cutting its power production in half every 5,730 years. Remember that quarks make up hadrons, and we spoke of hadrons with 3 quarks. Hadrons made of 2 quarks are called mesons. Mesons are composed of a quark-antiquark pair and are unstable, and break down to quarks of lower mass, giving off energy in the form of photons, and eventually into smaller stable particles, like electrons, neutrinos, and photons. Examples of mesons include pions, kaons, and muons. Pions are made of up and down quarks. Remember that one has to be anti. A pion can be made of an anti-up pair or an anti-down pair. This creates a neutral particle, as the 2 quarks cancel each other's charge. Or they can be mismatched, like an up quark with an anti-down or a down quark with an anti-up. An up quark has a charge of plus 2/3. A down quark has a charge of minus 1/3. So an anti-down would be plus 1/3, giving a positive pion a charge of plus 1. A negative pion is made of a down quark and an anti-up. The down quark has a charge of minus 1/3, and the anti-up has a charge of minus 2/3, giving it an overall charge of minus 1. That is why there is 1 negative pion, 2 neutral pions, and 1 positive pion. We now understand somewhat the strong and weak nuclear forces and their gauge bosons. Let's look now at the electromagnetic force. Matter is made of atoms. The nuclei of atoms are made of neutrons and protons. The nuclei are orbited by a cloud of bound electrons. Electrons are tiny stable particles with a charge of minus 1. Protons have a charge of plus 1. And neutrons are neutral with no charge. Atoms will usually try to have an equal number of protons and electrons, making the atoms also neutral. If there are more or less electrons than protons, the atom will have a charge. Such atoms are called ions. An atom with a positive charge is sometimes called a cation, and one with a negative charge is called an anion. The post in a battery toward which the cation moves is called a cathode. Positive charges move toward the cathode, so the cathode is negative. The post in the battery toward which the anions move is called an anode. Negative charges move toward the anode, so the anode is positive. It was found that if you built up enough electrical charge on the cathode, or negative terminal, it would start to fire particles. These were called electron guns. Not long ago, electrons were thrown through a near vacuum in a glass tube to impact a phosphor screen that would glow. This was called a CRT, or cathode ray tube. It is how old televisions and computer terminals were made. Liquid crystal display screens have a lighted panel with liquid crystals in front of them. By varying the electrical charge of the liquid crystals, we could change their orientation and color. These are still used in many automobile display systems, and they get sluggish when it's really cold. Then we found a way to make diodes emit photons. These were called LEDs, light-emitting diodes. The first ones were red, then it was possible to make green, and finally blue. This allowed us to make LED televisions even thinner than LCDs. The inventors of the blue LED were given the Nobel Prize because it allows us to combine all three primary colors and create white light. This is what most of us are using in our homes now to save electricity. When two pieces of matter approach each other, the particles of matter do not usually come in direct contact. The electron cloud around the atoms on the first piece of matter approaches the electron cloud around the atoms on the second piece of matter. When these clouds get close enough to each other, they exchange virtual photons. If the clouds were of opposite charge, the photons would pull them together. But since the clouds have the same charge, the photons carry the electromagnetic force and repel the two clouds. In a way, the matter in our bodies never touches anything made of matter. We just exchange virtual photons. Ion engines use these principles to create and eject ions, propelling a spacecraft forward. Now we have covered all the forces except gravity. That's enough for now. Please don't forget to like and subscribe. See the links to Patreon and the Academy store in the description. And don't forget to share virtual photons with your loved one tonight. At Astra Pro Terra.